Okay, so thank you very much. I was looking forward to this conference, but I should say that it exceeded my expectation. There are certain features which I think are remarkable. First, that days are organized by topic. So I honored to open a super day. And it's good because when you hear several things on the same topic, something remains in your head. And second, the breakfast is so substantial that you are discouraged to be late for the first talk. And of course, the last thing, I'm looking forward to Pavel's session, and maybe some of the open problems we will solve. I have some open problems during the talk, and maybe we will solve them. So maybe you noticed that there are two talks with the same title. So John Kuyava is going to talk about support variety for superalgebras, not supergroups. But what he's going to talk about is actually about homological support. And what I'm going to talk about is more about rank variety. So I have many collaborators. One of them is Alex Sherman, who by some reason is not here, although he promised to be here. And some other people which I mentioned. And in particular, we discussed a lot with Julia. We didn't write anything together, but I hope we will write something together about this stuff. Okay, so let me start from the beginning. And I am assuming that G is a group scheme in the category of supervector spaces. And I work over C, over C.
So it's not even affine at this point? Is it affine or?
It is affine group scheme, of course, yes, thank you. And so this is super-Tanakian category. And I thought a lot of, in the sense as Kevin in his talk. And if you heard the Sasha talk, there was this approach of Chandra pairs, and I would like to talk a little bit about it. So if you think about Hopf algebra of G, and you quotient it by, so everything is Z2 graded, and you quotient it by the ideal generated by odd part, what you get is the usual group, which is sometimes called body or underlying group. And this is the usual algebraic group, affine algebraic group over C. And what you can consider also the Lie, corresponding Lie object, which is a superalgebra. And you can, one way to look at the category of representations of G, and I'm going to consider rep G, which is finite rigid category, compact objects, and I'm going to consider rep tilde G, its int completion. Okay, so we're going to talk about both. And exactly like in Sasha's talk on Monday, one can think about rep G, or as well as this thing, as the category of G0 modules. Modules over the Lie algebra, which integrate to the action of G0. So the first theorem, I divided in two parts, and this is kind of old result. So I would like to see when the category of rep G is Frobenius, and the category rep G is Frobenius if and only if this underlying group, G0, is reductive. Okay? And G, and the category rep G is semi-simple. It's exactly known when the category rep G is semi-simple. When G, if and only if G is a product of some OSP 1 to some OSP 1, 2, and some reductive group. Okay.
Do you assume that your group is connected?
I mean, when I mean reductive,
This is Lie algebra. Yes, this is Lie algebra.
yeah, but actually, yeah, you could have disconnected, and I would like to have disconnected groups as well. When I mean reductive, I mean semi-simple category, which includes disconnected.
No, but you can have things permuting. We probably should say that this is just the Lie algebra.
Oh yeah, but you see, there is no discrete subgroups here, I think.
No, but
you can take
several copies, and then symmetric group can permute them.
Oh yes, yes, I'm saying this is connected part. We have connected part. Yes. Okay, connected part. I should say this. Right. Okay. Well. And what we want to do now, basically, we can study stable category, and we can do what Julia explained to us very nicely. We would like to build some Balmer spectra, basically, to discuss it. And one of the ways to fiber it over something, right? And my next subject is what would be analogous with cyclic. So actually, there is a lot of analogy with finite groups and positive characteristics, a lot of analogy. And one of the things which is natural to ask, what are cyclic group in this case? And what you can do, you can start in the odd element in G, and you can consider minimal algebraic subgroup which contains X. So this is minimal subgroup, supergroup. But and I would like to talk a little bit about this, what we can get in this case. So first of all, we have this nice identity.
So Lie algebra G contains X.
No, group, algebraic group. So it
No, but X is a Lie algebra.
All right, but I'm talking about Harish-Chandra person. Lie algebra, yeah, you say. Yeah, you are right. Lie G, such that Lie algebra contains G. You're right. So this identity here actually explains that G0 is abelian and central in the whole G. I should call this in central.
You mean brackets X0, not
Yeah.
G0. Because G is your big group.
Yeah.
Oh, no. Okay, thanks. Again, I'm sorry. Right, it's abelian and okay. Okay, so, so first of all, I would, so these groups, the group of reductive G0, we call quasi-reductive. This is a definition of the word. Okay, so the first thing that I would like to check when X is quasi-reductive, and you can actually tell this from taking the commutator of X with itself. And what I would like this thing to be semi-simple element in G0.
So reductive is linearly reductive?
I'm talking about linear reductive group. I'm over C. Okay, I'm over C. It's very interesting to do positive characteristic, but job should be done first over C because even in this case, it's not completely clear. Okay, so another thing which I would like to consider is the following thing. I start with rem G. I take restriction factor to, or actually I can work a little bit here, like this. And when I would like to take the semi-simplification factor. And I would like to, and where I end up, actually it's not difficult to show what in general, if I have such a group, the semi-simplification would be representations of OSP1, 2.
This is the quasi-reductive situation, yes?
No, quite the opposite. It is not in quasi. I mean, you always end up. You always end up, but what is happening? So I would like to now to give a name to such elements, and it's going to be homological. We call this element homological. This is all X such that the corresponding group is quasi-reductive. Okay, so I can consider such a.
In that case, the semi-simplification is just supervector space.
And then that's exactly what I want to say. Exactly what I want to say. But in this situation, the image of this functor is going to be in vector spaces. So it's only subcategory which consists only trivial representations of OSP. If X is in G1 home, then the image, let us call this functor Sx. Semi-simplification with respect to S, and Sx is target of is in image. I don't know. Image of Sx is in supervector spaces which are embedded in this category. Okay, and what is nice about this, I'm not sure I'm going to motivate. If I have time, I will motivate why I think it is nice. I can describe this functor in another way, and then it actually what I do, and then it becomes what is called DSX because it was some functor we encountered with Michel Dufour many years ago, and so.
Sorry, can the image be actually vector spaces?
I mean, okay. So if you take the arbitrary such group and just consider a semi-simplification without precomposing it, you end up in OSP.
No, yeah, but I mean the image can be smaller than supervec.
No. I mean, no, in some cases, yes. So there is a situation, since you asked, which we study with Inentova, Eisenbach, when this functor is actually exact. It's tensor, it's symmetric monoidal functor, but it's not exact. And it is exact exactly in the situation when for this X is important, and Jacobson-Morozov theorem is true for it. We call such element Jacobson-Morozov theorem in superversion. So it's exactly, so let me say that Sx, if and only if X is embedded in OSP1, 2, and we call such elements neat, but we are not going to talk much about it. It's a different story. Okay? So you can, but you cannot get more than OSP. Okay, so let me just give you homological description. So what you do, you take homology of X, which are X only, you take invariance with respect to the square of x, and you take the cohomology of this.
This is if x is homological.
X is 0 right now.
No,
I think
no.
this is the formula for x homological. Is that correct?
Yes, this is only for x homological. Yes, if x is homological. X is homological.
This is the semi-simplification functor in that case.
Homological. That's exactly. So this functor is just as another description of Sx. Okay? So you see, the point is that after I restrict my x to the invariance, it becomes x squared equals 0, and you can take homology. Okay. So if I look at this thing here, just this is conical G0 invariant subset in G1, but it is not closed at all, okay? It's not a nice variety. Sometimes it's dense, not always, but at least it's always conical, okay? Obviously. And so if M...
Sorry, Vera. I have a stupid question. How is this super vector spaces embedded in web OSP?
I mean, you just take trivial representation. Everything generated by trivial representation.
And so can you quickly say why the image is in there?
Quickly, the best way, I think, over here, actually.
So if you take an irreducible, non-trivial
okay.
representation and restrict to the stuff,
Yeah, so you
the
just...
dimension is 0.
So if you take representations of an element, so you take, so what is rep x, essentially, what is this? Those are representations of one odd linear operator, basically. So if it is homological, then it has two parts. The one part where x with non-trivial eigenspace, and there we are in a situation of Q1 and XX, and then it's obviously every irreducible representation is one-dimensional. And in the other situation, in the important piece, when it is 0, yeah, you have only things. Yeah, actually there is some interesting theory here. We are working on it for different important elements, but right now that's what I need. So suppose M is actually in the induced completion, then I can define Xm. Just the point in a homological part such that Sxm is not 0. Okay? So this is conical set, and this is my candidate for support variety, actually. So this is the candidate. Rank variety, I should say. But important thing is, although this thing is something strange, but you see, it is obvious that this thing is G0 invariant with the action of G0, so this is certainly G0 stable. So actually, I can take stack, which I understand rather naively right now, orbits with topology. But in many cases, this has a very nice description. Actually, almost always it has a nice description. And so I can also projectivize it. Okay, so I can actually think about support. something like this, okay? But maybe I write just down this for simplicity. And so what we see immediately there are two very good properties of support. One property is that it behaves nicely with sums and tensor products. And this is basically immediate since SX is tensor functor. And there are two important things which we have to check as projectivity criterion. Projectivity detection, yeah, let's go. And realizability, if I can say so. And I would like to talk only about projectivity detection today. So what this means, goal is to show M is projective, equivalently injective, if and only if its support in this form xm is just 0. Okay? And in one direction is obvious because whenever you restrict to a quasi-reductive group, projective goes to projective. And it is necessary.
What are you assuming about M?
Goal is a good point. M is actually, I would like it to be in rep.
So do you want to end up taking field extension?
Yeah, I mean, I will talk about it, Alex. Okay. So if I do here, there is some little thing, which I will explain on example very soon, actually, what Alex mentioned, that for realizability, you need a field extension, which I learned from Julia. I didn't really understand that before. Well, any questions so far? Right? Okay, hope it's clear all. So let us start with one example. So let us just consider this most stupidest example. So G doesn't has trivial even part, just G1. Then universal enveloping algebra of G1 is the exterior algebra on G1. And then what I'm claiming that lambda of G1 module is free because projective and injective is free if and only if it is free. It's if M restricted on C of X is free for any X in G1. So analogous statement in the theory of finite groups would be you take elementary abelian P group, and this is exactly the statement which was proven, as Julia told me, by Dade. I'm a little bit bad. And I think in our situation, it could be found in the paper of Avramov. But there is some subtlety here, which is very easy to see, that if my representation has very big, so at some moment in this proof, you use that any linear operator has an eigenvector. And that might be not true in general, right? There is some, some cardinality constraints there. So in general, if M is not countable dimensional, I need to extend the scalars. I should take extension also. This is up to extension to. Yeah, I should write it somewhere. I can't write here.
I have a question. So if you look at X from trivial module to itself, in this category, in the X spectrum, is it related to this XM?
Okay. Let me tell you. Actually, I hope that John Kuyava is going to talk a lot about it. No, maybe I'm sorry. Maybe not. But I think so because there is parallel process. I would say homological support by Dan Nakana, Kuyava, Bowie, and some other people, and it all started. But in the case of a simple Lie superalgebra, the cohomology we are talking about is a relative cohomology with respect to G0, and X1 is given by invariance, okay? Invariance of G0 in G1, the ring of invariance, which is very nice and most simple supergroups, simple quasi-reductive supergroups. So it is related, of course, in some way, right? But somehow, this is a little bit more. I have to consider all orbits. Okay, so yeah, it's certainly.
So that includes all the orbits which are not only the closed ones. Homological variety basically sees the closed orbits.
Yeah, so essentially, yeah. Before we wanted to call these elements semi-simple, but when we realized this is wrong, because there is a semi-simplicity notion of the closed orbit, and that's a different thing. That's why we consider this thing. Okay, what I was going to talk about. I should write that if M is infinite dimensional, and one have maybe extend scalar. Yes, extend scalars. Okay, so now I'm going to see what we actually prove this theorem.
Extension of scalars helps with non-existence of eigenvectors.
Because there is this thing which I don't remember whose lemma is it. Dix-Meyer lemma, right? There is this Dix-Meyer lemma, right? If you walk over C and your space is countable dimensional, any operator has eigen.
Yeah. So you assume that space is countable then?
Or I extend scalars. That's what people do. Okay? Or we can reformulate it slightly different way, but I need to.
Well, not any operator, but any, like if you have an irreducible module, then any endomorphism is a scalar.
Yeah. Yeah, that's exactly. Yeah, there's Schur's lemma in infinite dimensional settings. It's called Dix-Meyer lemma. And it is somewhere. Okay, so, well, so now let me explain. Maybe I should say right away that we have proved this goal. We have achieved this goal for G being Kac-Moody, say simple, a lot of G Kac-Moody, Kac-Moody simple, or Kac-Moody Lie superalgebra finite dimensional, like OSP and all this, and for rep G, we always have it. We have completely proved this for the arbitrary G. Okay, so I will now discuss a little bit. It's actually was.
But what is the first case when it's not known?
Like Q of n is a problem.
Q of n, and right now, there is this, okay, anyway, I'm trying to prove it more or less every night.
Okay, so tomorrow it might change.
Yeah, so that's a good thing to discuss if we have time.
You only have trouble for infinite dimensions.
Only for infinite dimensional. So let me now go to the proof, because, I mean, not the proof, but there is a lot of steps there. So, over C dimension, we can restrict ourselves to countable dimensional if you want, over C. Well, so the first thing which we developed of Alex was splitting subgroups. So let me start with the definition. So what is a splitting subgroup? It's analog of P group in theory of finite groups. So splitting subgroup, so K and G, both quasi-reductive. So we say that K is splitting A and G if I consider the induced representation from the trivial one, and I have the natural morphisms like this, and it splits. This morphisms splits. So I have invariant web in the opposite direction, such that the composition is not zero. Okay, so this standard thing is equivalent to saying that the restriction on X groups is injective. It's also equivalent to saying that if I have sequence in the realm G split it over H, split it over K, it splits over G. Okay? So actually I said the wrong thing. I mean, K is splitting in G for finite groups means that the index is not divisible by P. Okay? Okay, so, and two things. One, if K is splitting, and restriction maps in negligible morphism. Morphisms, the negligible morphisms. And in particular, that means, yeah, so we have functor of semi-simplification. Restriction gives you a functor of semi-simplification. Which is useful for some things here. And second, of course, suffice to check if restriction to K of M is projective. And M is projective. And we have a very nice geometric criterion when necessary condition is not criterion, sorry. So there is this proposition. that if K is splitting, then any homological home in a thicker orbit intersects the Lie algebra. So essentially, the set of orbits. So if I have any homological element and I take its orbit in G1, it lies in K1. And maybe I should say,
Not equal to 0.
Intersection of zero.
oh no,
Not
yes,
a zero. Not a-
not empty. Not empty. Okay, so, and this means actually very nice geometric proof. Maybe because I don't have many time to talk about proofs, I have some time.
So in what generality is this true? Is it like for Hopf algebra and Hopf subalgebra, or actually even maybe just algebra and subalgebra?
I mean, you mean these previous things? It's very general, actually.
So just algebra and subalgebra,
I
basically,
guess.
with enough projectives.
Yeah, something. I mean, up to this. This is, of course. I mean, I don't know, Pasha. I'm sure for groups in any category. I mean,
Well, negligible, you need a Hopf structure. Okay, so yeah.
I'm not sure. It's a good question, but maybe I'm not sure I can answer it right away. Okay, yeah, I would like to say a few words about it, because what I do, I'm actually talking about induction. And in this case, I'm talking therefore G mod K. And this is a homogeneous affine supervariety. And, well, so this have homogeneous affine supervariety, and we can think about X. And I can consider vector fields induced by X. So this is odd homological vector field. And if G0X intersection with K1 is empty, that actually means that X doesn't have fixed points on my variety. What part? What part of Lie algebra? What part of Lie algebra? X doesn't have fixed points. Okay, and in this case, it's kind of known result that there's no homology. So that means that ds x of O G mod K is 0. There couldn't be splitting. Okay, I should say, just advertise it, but with Alex, we also wrote a paper where we actually compute ds functors for different varieties, affine varieties, by localizing to fixed points. There are some useful results. So now next thing, I would like to actually say, so it was in this situation for quite a while, and then I went to Weizmann and I went Weitrop, and Weitrop got interested in super, and he was interested in super integration, and that's the next step. So basically, what we, in the finite group situation, we just take G mod K quotient and let's count the number of points. So here what we should do, we should take volume, okay? So I should take just a few words about integration theory. So if you are in the world of supermanifolds, then what you can do, you cannot take top differential forms, because there is no top degree. But there is a very beautiful analog. There is a special line Baldo or supermanifolds, which is called Berezinian Baldo. And here, if you came and you didn't know anything about super, so I promised Eric a tale about super. So Latest told me that Joseph Bernstein got interested in super after Latest was a Berezin student. So once he came to Joseph and showed him this formula and said, what you have to check, multiplicativity. This is an exercise, check multiplicativity of this. And Bernstein said, it couldn't be. But when he looked at it, he said, oh yes. So he took his head back and he started doing super. So anyway, there is a line bundle, analog of determinant bundle, and there is integration process. And you can integrate over compact manifold, supermanifold. So, and in principle, you can do something like a unitary trick. But there is one quite subtle point that Weintraub helped me to do. So anyway, let me first tell you the story. Okay, so we have this Berezinian sheaf. And in our situation, what we can do, actually it's another situation. So I take sections of Berezinian, and I take functions, and I have a perfect pairing. And it is given by the Berezin integral. I should explain how we do it. So you see, this is actually a complex manifold, but the underlying part has a compact form, cycle, C, compact form. Okay? And the point is that this is actually both are G shifts, and so this is invariant pairing. So it's perfect invariant pairing. So we now have the theorem.
So what is the subtle point? I didn't understand.
Subtle point is the following. So you actually should work what is called CS manifolds, which CS manifolds. Maybe you don't know. So there is no real compact form of the whole thing in most cases. But you consider complex functions on the cycle. So you need to do CS manifolds. And for example, localization formula, you have to prove it for CS manifolds. That's what we do with Dmitry. Because Schwarz and Zaboronsky proved it only for. I see this was a subtle point, actually. There is some analysis involved at some moment, some geometry and some analysis. But let me write down the theorem. So K is splitting in G if and only if G1K has K invariant Berezinian form, K invariant Berezinian, has G invariant. If Berezinian section and Berezinian section and what we call volume, Berezinian section that is called omega, and this Berezin integral is not zero. So basically, it's saying volume is not zero. Okay, and you can compute it again by taking a random odd vector field. And if you choose this nicely enough, there is a way to localize in this integral to points. But it's a geometric picture which I don't have time to explain. Well, so now, so one definition, a quasi-reductive G as called zero supergroup if it doesn't have proper splitting subgroup.
So I have a question. Why do you need to consider splitting subgroups as opposed to splitting subgroups for each individual element X? So there could be a subgroup which is not splitting, but for X, it has this property.
Yes.
Wouldn't it be good enough for you?
No, I don't think so. I think no, but I think no. So
we're trying to develop a theory of CELO subgroups. I mean, that's really what we're trying to do. And like, so if you think CELO subgroups are useful for representation theory of finite groups and characteristic P, that's just what we're trying to do.
He's my advocate, yeah. But we can discuss it. I have very little time. Let me finish, okay? So if it doesn't have proper splitting subgroup, and what we have, this theorem with the same authors that so G is X0 supergroup if G0 is lies in the commutator of G1 and G1 and and G doesn't have neat elements and G1 doesn't have neat element.
Neat is the one.
As in the beginning. Yes. Basically, it doesn't contain any OSP. And I actually could say what they are. So first of all, on these quasi-total groups, quasi-total. So there's quasi-total groups. So that basically means that a quasi-reductive satisfying these conditions, so they are quasi-abelian and reductive. And you can reformulate the statement about support by saying that if the restriction on any quasi-abelian quasi-total subgroup is projective and the module is projective.
And just because I think it's really beautiful, this is the analog of an elementary abelian subgroup in characteristic P. This is the direct analog.
Okay. So, but there are more. There are so-called takif supergroup. And fortunately, Kevin and Cheng actually studied it at some point. So what is a takif? And you can take products and some central extensions, but that basically, it is built out of this and this. And so what's takif is a very interesting thing. You start with G0, just simple Lie algebra. You take G1 is the joint representation and trivial representation. So I would say, maybe I discuss it like, define it like this. It's semi-direct product of so you take super loops in G0. So okay. So we have like two copies, G0, copy of G0, I'm out of time, yeah? Okay, so this is the takif. if you ask me, I say why it is very nice. The point is, it's very easy to prove projectivity criterion for if your minimal splitting subgroup is quasi-total, and this happens for all Kac-Moody. So for quasi-total is basically the example in the beginning, right? So quasi-total, it's straightforward. So for quasi-total, it's straightforward. So if split minimal splitting subgroup is quasi-total, which happens for all Kac-Moody cases. When we have it. Projectivity detection. In rep G, it is enough to prove it because you can reduce to GL case using. There is another geometric thing which actually, this is enough to check it for GLMN and go to, well, okay, sorry. So it's enough for, it's all, that's also enough to prove for FG. So now what we can do, we can prove this projectivity criterion for this Takif, okay? Although I think maybe I have some ideas how to do it. And the last thing, we believe that the Silo theorem for supergroup is true, but if I have two minimal splitting subgroups, then they are conjugate. And we checked it in many cases. Oh, thank you.